Okay, so now it's recording. Good morning. Welcome everybody to the uh, first part of our fifth lecture. So this is the end of the first week of the course, and today I hope that we'll finish or get very close to the end of what I called in the first day old quantum mechanics, namely all this description of weird phenomena that people started to see and understood that classical physics should be, replaced, or rather, complemented by something else, which is quantum theory. So today, I want to discuss with you a very important achievement of this, let's say, old quantum theory, which is the atomic model put forward by Niels Bohr. So I will start sharing my screen. Just a second. Okay. Okay. So I hope that you can see my screen. Do you see? Can you let me know? Okay. So you see my screen. Great. Okay. So just a short recap of what we did yesterday. So yesterday we discussed about. So I don't know what is going on. So it seems that my notes disappeared. Just a second. I will stop sharing and share it again because this seems to be a problem. One moment. I hope that I get the notes back. Yeah, so it seems to be working now. Just a moment. Okay, do you see my notes? Okay, good. So now it's working. Okay, thank you. So yesterday we were discussing about the fact that if you direct a light ray, white light ray, towards a prism, then this light ray would be outgoing in a, it will be wider and also decomposed in different colors. And we call that the spectral decomposition of the radiation. And we have discussed that, in fact, if you repeat the experiment with sunlight, you're going to see the spectral decomposition of sunlight, and that some colors will be missing, right? So you're going to see some dark lines in the spectral decomposition of the sunlight. And we discussed that this is due to the fact that in the solar atmosphere, there are some atomic species that will absorb these colors, and therefore, when the radiation comes to the Earth, these colors will be missing, and we are not going to see them in the spectral decomposition. And then I talked to you that this is in fact a property that you can see if you pass light through some glass tube filled with some sort of gas. And in particular, I was showing to you what happens if you use the gas of being made of hydrogen atoms. And I told you that for the hydrogen atom, which is the simplest atom we can think of, we'll see these dark lines in the absorption spectrum of hydrogen. But also, we could heat this gas of hydrogen and make hydrogen to emit radiation. And you're going to see the emission spectrum of the hydrogen. And the picture that you're going to see is complementary to the picture that you saw for the absorption spectrum. So those colors that were missing for the absorption spectrum will be those colors that will appear in the emission spectrum, okay? And what we saw is that these frequencies or wavelengths that are missing are rather not a continuum range of colors, but a discrete set of wavelengths and frequencies, okay? And as I told you, a high school teacher, Jochen Baumer, described how to compute the wavelength of the missing color by using this equation here that is generalized to this equation here, where once you choose the value of m, you have to choose those values of n that are given by these possibilities here. So m plus 1, m plus 2, and so on. So this will give to you the missing spectral lines in the absorption spectrum of hydrogen. And in front of this equation here, you see that there is this constant, which is called the Rydberg constant. That was a constant introduced in order to tune the equation in such a way that you reproduce exactly the values that you see in the lab. So this is an equation that you did not derive from a more fundamental theory, but rather, I mean, you just, Baumer just stared at the pattern of the absorption spectrum of hydrogen and started guessing what would be the formula that would describe what he was seeing. But of course, I mean, as physicists, we would like to explain this formula from first principles because, I mean, this is specific to hydrogen. But if I want to, describe a completely different atom and a completely different chemical component, how do I derive the expression that gives to me the spectrum of such an atom? Okay, so this is a difficult task, but let's start with the simplest thing. The simplest thing is to explain this equation from what we know from physics, what we know about the dynamics of the atomic structure, and try to find out if we can derive this expression. And the first step, and actually it was a very important step, was given by Niels Bohr. So Niels Bohr, I think it was around 1913 when he proposed his model. The units, okay, so Mahmoud is asking if the units of lambda is in meters or centimeters. Actually, it doesn't matter. You can use both. But look, this value that I gave to you for the Rydberg constant is given in centimeters to the -1. So if you plug this value exactly there, you're going to express the wavelength in centimeters. But you can just, change this expression here from centimeters to the -1 to meters to the -1 or nanometers or whatever unit you want. You just have to be careful with the value that you replace there. Okay, so Um, okay. Yesterday, I explained to you that Rutherford discovered that an atom would be made of a tiny nucleus with a positive charge and with electrons around it in a cloud. Okay. Um, and this model seemed to be correct in view of those experiments that I described to you with alpha particles being thrown against the gold foil. Okay. So now we want to understand, I mean, given that this is the proposal, you have a nucleus with positive charge and you have electrons going around it. We want to understand what the classical theory tells us about that. And this is a challenge, a conceptual challenge for the classical theory. And the reason is the following. Um, when you have this model that was described by Rutherford, let me go back. So you are going to have negative charges essentially rotating around the nucleus. Okay. So these charges, which are the electrons, they are accelerated in the sense that their velocity has to change with time, namely has to change the direction in such a way that they keep in a circular motion. Okay? So there is an acceleration. And maybe some of you don't know that, but for those that know and for those that do not know, I'm just going to make a statement about Maxwell's theory of electromagnetism. And the statement is the following. If you have an electric charge and this electric charge is accelerating, then the electric charge will emit radiation. Okay, so this is a prediction made by classical electrodynamics. And here I'm saying to you that we will have electrons moving around the nucleus. And since they are moving around, they are accelerated. And if they are accelerated, according to Maxwell, those particles will emit radiation. But if an electron emits radiation, then it loses energy. Okay? And if the electron starts to lose energy, it will start getting closer to the nucleus and closer. And at some point, the electron will just fall in the nucleus, and you're going to collapse the atom because you're going to collapse positive and negative charges. So matter made out of positive and negative charges would not be stable because atoms would not exist for a long time. Okay? So this is a huge problem when you take seriously this model by Rutherford. Okay? However, there was empirical evidence for the existence of such a nucleus and that electrons were moving around it. So how to deal with that? Okay? So immediately looking at Rutherford proposal, we have this conceptual problem about the stability of matter. So the atom would just collapse if you take too seriously the model as it is. So Bohr started to think about on how to deal with such a problem. And in order to do so, Bohr considered that one, accelerated electrons will emit radiation. This is a prediction by Maxwell's theory. And he wanted to describe the simplest motion that you can think of, which is a circular motion of electrons in a hydrogen atom around the nucleus. So he used Newtonian mechanics in order to describe the motion of electrons, okay? But of course, Bohr knew that if he just did that, then the electron would fall in the nucleus and everything would not make sense. So he had to do something else. And I'm going to explain to you what he did, okay? So we are going now to discuss the atomic model proposed by Bohr that introduced, I mean, a very important concept that will be, you know, the basis of the quantum theory. So let me move to the next page. And in the next page, you see a model for the hydrogen atom. So I have the nucleus here in red. It's a tiny, tiny region. And this nucleus contains a charge that is the absolute value of the electron charge. And the atom contains just one electron that is moving in a circular motion around this nucleus. The fact that I'm choosing a circular motion is just to make things easier, but you could consider, for instance, an ellipse or an orbit, a more complicated orbit, okay? Good. So first, you have to understand why the charge in the nucleus is the absolute value of the electron charge. Well, the atom must be electrically neutral. So the charge here must be the opposite of the charge of the electron. And the electron has charge minus E. So the charge inside the nucleus should be plus E. And the electron has a mass that we are calling in these lectures as ME, okay? Now I want to describe, according to Newtonian mechanics, what is the equation of motion for this electron, okay? Before I explain that, I want to do a brief recap about Newtonian mechanics and also classical electrodynamics. For those of you that don't remember, please take that as an opportunity to ask questions, okay? So before I explain this equation, let me tell you some facts about the classical dynamics. So Newton has proposed that given a particle that want to describe the motion, the total force that acts on this particle, so if you take all the forces that are acting on this particle, and remember, forces are vectors, and the total force will be the sum of those vectors. So if you compute the total force of this that acts on this particle, these will be equal to the mass of this particle times the acceleration of this particle. And here I'm just looking at the absolute value of the force and the absolute value of the acceleration, or the magnitude, okay? But of course, this equation holds as a vector equation, so I can just remove these bars here and write that the total force vector is equal to m times the acceleration, the vector acceleration of the particle. So this is Newton's law that describes the motion of a particle. And remember, if you remember the details, this equation is valid for reference frames that we call inertial reference frames, okay? If you have non-inertial reference frames, then you have to take into account fictitious forces, but we are not going to discuss that here. So I'm just assuming that I have an inertial reference frame, and by definition, those are frames where Newton's laws are valid. Okay? Now, I'm going to move to another important concept that you probably have learned before, even in high school, which is the fact that if I take two charges, okay, Q1 and Q2, so I have here Q1 and Q2, and I place them in such a way that they are separated by a distance d, um, Coulomb told us that these charges, which are particles with some electric charge, will um, uh, try to repel or to attract each other, depending on the sign of the charges, via an electric force. And do we know how to compute this force? Yes. So these particles, if they are at rest or if they are moving very slowly, they will exert a force on the other, which is given by the Coulomb law. And the Coulomb law says to you that the magnitude of the force that Q1 will exert on Q2 or the other way around will be a constant, K. So this is a constant that depends on the system of units that you're using, but this is a constant that you measure in a lab, okay? Then you take charge 1, take the absolute value of charge 1, take charge 2 and take the absolute value of charge 2, multiply these values and divide by the square of the distance that separates those charges. Is it possible that, is it possible that it will move circularly without so here I don't have a magnetic force, I just have the electric force. And you see that I was going to say now that this Coulomb force is a force that acts on the line that connects those charges. So since these are charges of different signs, then the Coulomb force will act along the radial line, and it will try to attract those charges. So if you wish, the force exerted by the nucleus on the electron will be on the radial direction. Will be something like that. Okay, so this will be the force. And because you have a force that acts on the radial direction, this force will have the power of changing the direction of the velocity. So this force will produce a radial acceleration that will make this particle to move in a circular orbit. Okay, does it answer your question? Okay, good. Okay, so we know now how to compute, how to relate the force with the acceleration of the particle by Newton's law. We know how to compute the electric force that the nucleus will exert on the electron by Coulomb's law. And we can also derive that if you have a body in circular motion, then the acceleration of this body will be in the radial direction, will be in this direction here. And this is called the centripetal acceleration that is given by, this should be, this should be v squared. Okay? So the centripetal acceleration will be the absolute value of this velocity, which the size of the vector is constant. Okay? So the magnitude of the velocity is constant. So this is a constant number divided by the radius of the trajectory. Okay? And And a final comment, because I will use that soon. If you have a system that is composed by two charges, then the system stores some amount of potential energy, in this case, electric energy. And if you want to compute the value of this electric energy, you just use this expression. So you take minus k, the same k that appears here in Coulomb's law, and multiply by the absolute value of those charges divided by d. Okay? Good. So I hope that this short recap will make things clear to all of you. But now, let's go back to this first part of this slide and apply Newton's law. Okay? So I will apply that the force is equal to the mass times the acceleration. So what is the force that the nucleus will exert on the electron? Well, it's just the Coulomb force. Okay? So this will be K times the absolute value of the charge of the nucleus times the absolute value of the charge of the electron divided by the distance squared. Okay, so there are some questions. I'll just go to these questions, just a second. So this force will be equal to the mass of the electron times its acceleration. So the force is written here, K times the first charge times the second charge. So the absolute value of this charge is E. The absolute value of this charge is E. So you have E squared. Okay. And it will be divided by the distance between these two charges. Okay. The distance between these two charges is nothing but the radius of this circumference. So this will be divided by r squared. But according to Newton's law, this must be equal to the mass of the particle, namely the mass of the electron, times its acceleration. So this must be equal to the mass of the electron, me, times the acceleration. But since this is in a circular motion with constant speed, then the acceleration is the centripetal acceleration that's given by this expression here. So I multiply the mass by the square of the speed divided by the distance or the radius of the trajectory. So this is just a direct application of Newton's law. Okay? Force equals to mass times acceleration here. Okay? Well, there is an r here, there is an r squared here. I can simplify and write that me, absolute value of the velocity squared, is equal to k e squared divided by r. So I arrived at this relation here just by applying Newton's second law. Okay? So before moving to the next slide, let me check the questions in the chat. Is there a reason for the minus sign for the electric potential energy? Yes. You see that here I'm talking about a system that has charges of different sign. Okay. So if I have a system with charges of different sign, these charges will try to attract each other. Now, if I had a system with charges of the same sign, then they will try to repel each other. So it cannot be that the energy of one system, the first system, is the same of the other system, because one is making the charges to get closer and the other is making the charges to get apart. And the key aspect that will characterize this for you is this sign. Okay. In other words, you can derive the expression for the potential energy by using the relation between the Coulomb force and the work that it realizes when you transport a charge from one point to another point. Okay, and you get the correct sign by doing that. So it's not let's say a trivial thing. You have to understand these details from the calculation of the work that is realized by the Coulomb force, okay, or the force that you realize to win against the Coulomb force. But I can explain that in more detail at some point if you want. Let me see. Please, how do we get the explicit value for K? So the explicit value is obtained by an experiment. So you just place two charges that you know the value. So for instance, you place two electrons separated by a distance that you know, and you can measure the force that one electron will make on the other, will exert on the other electron by using some equipment that measures the intensity of the force. With that, you can measure how much is K. Okay, and as it was written in the chat, in natural, sorry, not in natural, in the international system of units, this K is just 9 times to the, well, it's, yeah, I think it's 9 times 10 to the, now I'm confused because it's written 10 to the minus 9 in the chat, but I was thinking that it was 10 to the 9th. Maybe I'm confused. So let me check. Just a second. Yeah, so as I said, it's not 9 times 10 to the minus 9, but rather 9 times 10 to the 9, okay? In the standard units. And of course, you can rewrite that as it was written in the chat. I mean, you can write K. You can call it as another constant, which is this one, where this parameter epsilon 0, epsilon naught, is a parameter that depends on the medium that the charges are placed. And if you remember the very first lectures, you see that we encountered this epsilon 0 before. So this comes from Coulomb and propagates until Maxwell's equation. But I don't want to discuss all of these details. For the moment, you can just think of this as being a constant that we know the value. Okay? Is ME the mass of the electron or the nucleus? The mass of the electron. So ME represents the mass of the electron. So when you apply Newton's law, the mass that you place here is the mass of the particle that you are describing the motion. In our case, it's the electron. So this is the mass of the electron. Okay. Okay, so Elise raised the question about what about the case where the charge is being, you're taking from from infinity, so that so let me answer this question with a short comment, which is the following. Physically, the value of the potential itself has no meaning. What has a meaning is the potential difference, okay? So when you write that the potential energy is given by that, I can, I can add a constant here, and this will not change anything on my physical conclusions. Because what matters for physics is the difference of energies. So you probably have learned about gravitational potential energy. So I can ask, what is the gravitational potential energy of this pen when I place this pen at this height? And you learned that the potential energy will be the mass of the pen times g, which is which is gravity, the acceleration of gravity, times the height of the pen with respect to the ground. But then I can ask you, which ground? I mean, I am here sitting on the 3rd floor of the building, and I live on the 9th floor of my building. So if I compute the energy here, I will measure the height with respect to the floor of this room. And when I am in my apartment, I will compute the potential energy with respect to the floor of my apartment. So, I mean, how can it be? It turns out that the value of the potential energy of this pen, it's meaningless. What is physically meaningful is the difference between the potential energy of this pen with respect to some point and to another point. And you see that the variation of the potential energy is what is meaningful. And therefore, I mean, if I place the ground with respect to which I compute the potential energy and I change it to another ground, I mean, the value of the potential energy itself will change, but the variation, when I take this pen from this point to this point higher, this is what physically matters. So the value of the potential energy in a single point, it's not that important. So here I am assuming that the potential energy at infinity will vanish. So I'm just taking a reference where I say that the potential energy is 0 at infinity, as I can say that the gravitational potential energy of this pen with respect to the ground of my office here is 0. Okay. This is maybe I made a lot of this confusing discussion about that now. I started talking a lot about this, but my point is physics is placed on the difference of potential energy and not on the particular value of the potential energy in one single point.
Hello.
Hi.
Yes, please. Back to Rutherford model and Maxwell statement.
Sorry, can you repeat your question?
Back to Rutherford model and Maxwell statement.
Yeah.
I don't know who said that accelerated charged particle lose energy and then the atom will collapse. Who said this? Oh,
Maxwell said
according to what?
Maxwell said that an accelerated charge will emit radiation. And when it emits radiation, it loses energy. So if it is losing energy, it starts falling towards the nucleus. Okay?
Okay, who said the electron accelerated in this atom?
So Maxwell said that accelerated charges will emit radiation. Yeah. Does it answer?
No, my question about who said the electron inside the atom are accelerated.
So the electron here, they are in a circular motion. Okay. So do you agree that in order to have to perform a circular motion, the electron has to change the vector velocity?
Okay, you mean the centripetal acceleration?
Yes.
Oh, okay.
Yes.
And he used the concept of losing energy according to quantum.
No, Maxwell predicted the emission of radiation in the classical theory. So this is a completely classical statement. What will happen is that Bohr will connect that to quantum.
Okay,
Okay,
thank you.
you're welcome. There is another question in the chat, which is this motion, in this motion, does the nucleus emit positive charge? So the nucleus does not emit charges, okay? So the charge is inside the nucleus and stays there. Prince, does it has a value? You mean, were you referring to the constant that we were discussing before? Yeah, so K is it has a value, it's 9 times 10 to the 9. Well, you have to work out the units. It will be Newton times meter squared divided by Coulomb squared. And with that, you can compute the value of epsilon naught, because you can just plug here 9 times 10 to the 9, multiply by 4 pi, and then invert the expression in order to obtain epsilon naught. So it's not, it's something that you measure and then you can, okay, it's clear now. Okay, good. Okay, there are more questions. That's good. Let me see. I think that is an implication of the Rutherford model of the atom if you consider the Maxwell theory. Silas, can you, because this is the trouble with those questions. I mean, I cannot recall what I was saying when you wrote that. Can you elaborate on your question? Okay, so you're talking to, okay, good. And then there is a long thing, let me see. The paradox of a charge in a gravitational field is an apparent physical paradox in the context of general relativity. A charged particle at rest in a gravitational field, such as on the surface of the Earth, must be supported by a force to prevent it from falling. According to the equivalence principle, it should be indistinguishable from a particle in flat space-time being accelerated by a force. Maxwell's equations say that an accelerated charge should radiate electromagnetic waves, yet such, and it's not. Okay, so I think you are raising the following point. I'm saying that accelerated charges emit radiation. But now, assume that you move to a reference frame that is also accelerated and walks together with the charge. So with respect to this accelerated frame, the charge is at rest. And then you can say, well, in this reference frame, is the charge emitting radiation or not? Because now it is at rest. Well, all these statements that I'm making here are with respect to inertial reference frames. And most importantly, I'm disregarding completely the effects of the gravitational field. So I'm not talking about general relativity here. So this question, maybe we can discuss, if you're happy with that, we can discuss this question again when you learn more about general relativity in the other lecture. I think that's a nice meeting point between the courses. We can discuss. Of course, this is not a question about quantum mechanics. This is a question about classical electrodynamics, but we can discuss. Okay. Is that fine for you? So I will assume that I did not see any reaction, so I would assume that it is okay. Okay, good. So just to recap, because we had several different discussions, just to recap, I'm just saying to you that if you have a charge that accelerates around a negative charge, which is the electron, moving around the nucleus, which has positive charge, then according to Newton's equation of motion and Coulomb's law, this relation must hold. So me speed squared must be k e squared divided by r. Okay, so this is something that we are going to use in the next slides. So now I can ask you, what is the total energy of the system, namely this atom? You have a nucleus that is at rest, but it contains a charge. And you have an electron that is moving around the nucleus and also has a charge. So you have to consider the kinetic energy of the electron because it has a velocity. And you also have to consider the electric energy between that is stored in the electric field produced by the charge in the nucleus and the electron. So if you now write the expression for the kinetic energy of the electron, this will be 1/2 mass of the electron times the speed squared. This is the expression for the kinetic energy, okay? Plus the potential energy, the expression for the electric potential energy that I just explained to you one slide before, which is minus k e squared divided by r, okay? So this is the total energy of the system. Now I can just, you remember that before we related mv squared with k e squared divided by r. And here I have an expression that involves mv squared. So I can just replace the expression that I had before here for mev squared in this expression. And this will give to me k e squared divided by r. And I had this factor of 1/2 in front of it. So I have this factor 1/2. And I just repeat this expression here. Now I can sum these two terms, and this will give minus 1/2 k e squared divided by r. And this minus k e squared divided by r is nothing but the value of the potential energy. So the total energy of this system is minus 1/2 of the electric potential energy. Okay? So I'm just expressing the total energy as a function of U. Okay? So far, I'm just applying classical mechanics and Coulomb's law. And I have now an expression for the energy of the system. Okay? So when the atom emits radiation, namely when the electron is accelerating, so the electron will emit radiation according to Maxwell, the energy of the system will decrease. So the atom is losing energy to the outside. So and we have an expression for the total energy of the system. So this energy E, which is minus U/2, will decrease after the emission of radiation. So Bohr associated the variation of the energy, namely the fact that the electron is sending out energy. Oh, there is a question, why is minus U? y is minus u over 2. Yeah, maybe you are correct. Yeah, because I mean, if I say that, yeah. So if I'm defining the potential energy with the minus sign, then yeah, you are correct. So this should be a plus. Okay, thank you. Um, yeah, you are correct. Okay, so thanks. What Bohr did was the following. He associated, it is negative, so I'm lost now. Okay, I will fix this sign later, but let me move on, because this is something. No, this is negative. This we agree. But the definition of the potential energy is with the minus sign. So this will be U over 2. But this is negative. No dispute. Okay? Do you understand? Okay. So what Bohr did was the following. He associated the variation of energy by the emission of light. Okay, so the electron will emit radiation. So he associated that with a variation of the radius of the trajectory of the electron. So this is not trivial, okay? What Bohr did was the following. He said, when the electron emits radiation, it will move from this trajectory, which has some radius r, to some trajectory that has a smaller radius, but that will still be a circular trajectory. So the electron jumps from one trajectory to the other. And then you can say, but this is completely, why the electron cannot move continuously towards this one. This is not what happens. Bohr proposed that the electron really jumps from one trajectory to the other. Okay, I'm going to explain that in more detail soon, so don't panic. Okay. So if I want to compute what is the variation of the total energy of the system when the electron moves from an initial radius to a final radius, I can compute the energy that the electron gave away. So this will be the initial value of the energy minus the final value of the energy, okay? So we know how to compute the energy is given by this expression here. So I just write this for Ri, namely the initial radius, and just repeat this expression for the final radius, and this will be this expression here. When I subtract this from this, you see that I have this minus sign because I'm, taking the difference. So this minus with this minus becomes a plus. And this expression here, if I put ke squared divided by 2, if I factor out this expression reduces to this one. So what Bohr is saying is that when you move, well, this is true irrespective of jumping from one trajectory to the other. If your electron is in one trajectory with radius Ri initially, and it goes to a trajectory with radius Rf at the final state, then the variation of the total energy of the system will be this one. Okay, this is just a simple calculation. You just take this expression evaluated at Ri, this expression evaluated at RF and just subtract one from the other, and you obtain this. Okay? There is a question in the chat. Is the trajectory same? Yeah. So when I say orbit and when I say trajectory, this is an orbit, and when I say orbit, this is so these words have the same meaning in this discussion. Okay. Okay. So this is an expression that comes out from Newton, from classical dynamics. And now comes the key point. I will mention that, and we are going to stop for the break. Bohr was aware of these developments about the photoelectric effect and so on. So what Bohr proposed was the following. The electron will emit radiation, and we learned from the photoelectric effect that radiation is composed by photons that carry energy of equivalent to h nu. Okay, this was essentially what we discussed through this week. So Bohr said, if an electron emits radiation, then it loses the energy equivalent to the energy carried by a photon. So this is a very bold assumption. So Bohr said, this energy difference that I compute must be equal to the energy of the photon that was emitted by this electron. Okay? So Bohr says this variation, delta E, is equal to the energy carried by a photon, h nu. Okay? And of course, I can rewrite nu as C over lambda, as we discussed. So what Bohr concluded was that this variation, well, it was not a conclusion, it was an assumption, that this energy must now change. So the energy changes in this very particular way. So when you change the energy from an initial state to a final state, this difference, if you change from an outer orbit towards the center of the atom, then the change in the energy was h nu. Okay, so I will stop here for the break and continue the discussion. But there is a question in the chat. Let me look at it. If the electron moves in a circular path, what accounts for the different radii? Yeah, so the electron. So if you ignore the fact that Maxwell told us that accelerated charges should emit radiation, then the electron would be moving, in a circular path forever with the fixed radius. But Maxwell told us that the electron will emit radiation. And if the electron emits radiation, it loses energy. So the electron cannot create energy. It is giving away energy. And if it's giving away energy, then the radius of the trajectory will shrink. Okay? This is what accounts for the change of the radius of the trajectory. Okay? Okay. So I will stop now for our 10 minutes break. And then I'm going to come back to this discussion because this is a very important part. Okay? So we see each other again in 10 minutes.